Hello everyone. Yesterday we derived a set of three equations that we are calling the kinematic equations. Kine, remember, is the Greek prefix for motion. So these are quite literally the equations of motion. Right? Although they are only of a specific kind of motion, that is uniformly accelerated motion. Right? The kind of motion that we have been examining so far in this unit. And here are the three equations. The first one says the final velocity is equal to the initial velocity plus the acceleration times the time. The second equation says that the displacement, final minus initial position, is equal to 1/2 the final plus the initial velocity times the time. Remember, this one is really just average velocity times time. Right? If we take the final and the initial, add them up and divide by 2, that's the average velocity. And then the ever popular and very useful third kinematic equation is displacement, or final minus initial position, equals the initial velocity times the time plus 1/2 the acceleration times the time squared. Right? Got to be very careful when using these, that these are vector equations. Positives and negatives, if we're in one dimension, are very important here, and that we do have a squared on that t, right, on that particular time. Now, traditionally, there is a fourth equation. Right? We created a set of these because it helps us to problem solve, because each equation is missing one thing. If you look at the first equation, there's no displacement in that equation. If you look at the second equation, there's no acceleration. The third equation lacks the final velocity, which is there and there. So the traditional fourth equation lacks time. So it'll have the other variables in there in some combination, but it won't have any t's, right? No times. So what we are going to do today is we're going to do a little bit of a lab extension. We're going to take the data that we figured out by doing our Pivot Interactive, right, and our lab extension on our Pivot Interactive, and we're going to create this fourth kinematic equation experimentally, after which we will then do it theoretically. So we'll be able to see this both ways. And then we'll have a complete set of kinematic equations. So this one, the fourth kinematic, traditionally relates the final velocity to the displacement of the object without time. So its final velocity and displacement are the variables we're going to look at here. And whether you know it or not, we had those variables already. So here we have velocity, remember, is a v with an arrow. Displacement is delta x, change in position, otherwise known as final minus initial position. And so the purpose of this lab extension, and hopefully at this point either Mr. Jackson is giving it to you or you are printing off the lab extension sheet. Right? And it's to create, the purpose is to create graphical and mathematical representations of the relationship between, again, velocity and the displacement for the dry ice puck on a ramp, which we now know is moving in uniformly accelerated motion. And along the way, we're going to figure out what the meaning of that slope is, right, in this graph, but we'll get there. So I just wanted to remind you of where we started with all of this, and that was analyzing a dry ice puck, right, sliding down an incline. And we found that that dry ice puck actually accelerated. Remember, acceleration is how quickly your velocity is changing. Change in velocity over change in time. Right? And we figured out that acceleration. And that's all information we're going to use as part of this lab extension. So if you have your lab sheet out and you've got your lab and lab extension from the earlier part of the unit, we can start to use that data to develop a relationship between velocity and displacement. So, first thing we need to do here is I need you to go back and look at your dry ice puck on a ramp lab and your dry ice puck on a ramp lab extension, and I need you to pull out the data that you found in your Pivot Interactives. You don't need to redo the Pivot Interactive, hopefully, if you still have the lab sheets, right? You just have to write everything in. So fill in this data table, right? And I would suggest you pause the video at this point, and when you filled it in, come back and we'll move on from there. All right. So if you've got the data table filled in, our next step is we're going to use graphical analysis to make some graphs. So you've got to get that data table, right, this data table, into graphical analysis. If you've forgotten how to use graphical analysis, data analysis with graphical analysis is the sheet you want to look at that'll help you figure out how to do things like format the column headings, right? Put in the name, time in seconds, displacement in centimeters, and velocity in centimeters per second. I'll tell you how to get that third one in here in a moment. Starts out with only 2 columns, right? So change the column headings, do all that. Follow the sheet if you need help. To get the third velocity column in there, okay, you need to go on graphical analysis and click on the 3 dots next to the displacement column heading, which hopefully you've put in there, right? That'll be the y-axis, I believe. No, sorry, the x-axis actually. And you're going to put this in, and you're going to click on that, and then it's going to give you some choices, and you're going to choose Add Manual Column. Once you do that, a third column will pop in there, and you can go in and change the column headings, format it, to be velocity in centimeters per second. So go ahead and get your data table set up in graphical analysis. Pause the video and come back when you're ready. Okay, you've got your 3 columns now. Hopefully you've got column headings and units so you know which are which. All right, so in order to do the purpose here, to fulfill the purpose, we need to create a velocity versus displacement graph in graphical analysis. If you've forgotten how to do that, I would suggest at this point that you have a single graph and the data table open, right? Because you can set up different things that way. And then use velocity and displacement. Now, this is the way I want it set up, all right? So it's kind of hard to tell. We're doing a lab extension. What's independent, what's dependent. I would like you to put the velocity on the vertical axis in centimeters per second and the displacement in centimeters on the horizontal axis. Okay, so go get your lab set up, or sorry, your graph set up, right, with the right axes. Pause, come back. Okay, if you completed your graph, it should look something like this. Does yours look like that? This is what is known as a side opening parabola. You notice the openings over here, right? Now, if you got a top opening parabola, top opening, right, then your axes are backwards. Then you didn't put your velocities on the vertical and your displacements on the horizontal. You did them backwards. You either typed them in backwards or you just put them in backwards. So go back and fix them till you get this shaped graph. And if you got a straight line, you really didn't graph the right things. Right? So make sure you're graphing velocity and displacement. Well, you'll notice here that it's a curve. And since it's a curve, what do? We linearize. So I now want you to create a linearized graph of this. Now, how do we linearize? We do that by manipulating one of the variables. 3 choices we usually see: squaring, square rooting, and inverting 1 over. Normally, when we've linearized, I've had you work with the horizontal variable, the independent variable. This time, though, because I know the equation I want to get at the end, okay, it saves us some algebra, I want you to do something to the velocity. Okay? So when linearizing this graph, do something to the velocity, not the displacement. All right? Follow the steps on the back of the data analysis with graphical analysis sheet if you need it. Pause it. Right? And when you're done, you should have 2 graphs. A graph that looks like this on top, and then your linearized graph on the bottom. So if you try to do something to the velocity and it doesn't linearize the graph, you got to try something else. All right? You got basically 3 chances, 3 choices. Okay. So if you linearized your graph, you should have seen something like this, I'm hoping. Here's my graph. This is actually, I went in and did the data myself inside a pivot. So this was my data, very quick run at the data. And here's my side opening parabola. If you're just seeing, by the way, on yours, if you're just seeing the dots, you can go down here, click into graph options, and turn on both lines and dots so that you can kind of see the pattern. All right, and there's our side opening. So notice here what I had to do to linearize this graph. I squared the velocity in units of centimeters squared per second squared. Right? If you square the variable, you've got to square the units as well. And that created a linear graph. Notice very linear, not perfectly linear because there's some error even in a pivot, right? But 0.9995 is my correlation. So this is a pretty linear graph with a slope of about 714 and a y-intercept, which is 123, which isn't really significant because look at how huge these numbers are, right, on the vertical axis. So it's way less than 5% if I maximum here. So did you get numbers like these, right? Did you get a correlation of close to 1, I hope? Did you get a slope of, you know, around 7 to 750, somewhere around in there? Right? If you did, then everything's working well. So the resulting graph, our linearized graph, is linear, 0.9995, and it goes through 0, 0. So what does that tell us about the variables? When you graph two variables and they result in a graph which is both linear and contains 0, 0, we can say those variables are proportional to one another. And it's not velocity and displacement. That didn't result in a linear graph. It's velocity squared and displacement. Now this one's a little different, right? We haven't really seen this kind of relationship before. Basically, if you want your dry ice puck to go twice as fast, it would cover 4 times the displacement, 2 squared. If you wanted it to go 3 times as fast, 3 squared, 9 times the displacement is what it would take. This can also be done the other way. There's another way to linearize this graph. You could have, instead of squaring the velocity, you could have square rooted both sides of this. You could have square rooted the displacement. You would have still gotten a linear graph. It's just that you would have gotten a different slope because you're graphing different things, right? And again, the reason I chose to have you work with the velocity is because I know what equation we're heading towards, and I want to save us some algebra. Okay? So here's the relationship we found. The velocity squared is proportional to displacement when you have uniformly accelerated motion. But then the kind of begs the question then, well, if velocity squared versus displacement is linear, one of the things we often look at on these graphs then is slope, right? So what does that slope tell us about the motion of our dry ice puck? Right? What does that tell us about the motion? What does it represent? Well, sometimes units can give us an idea. So let's look at the units of this slope. Of course, we find units by going rise over run, right? Just like we find a slope. So the units of rise, centimeters squared per second squared, right? Remember, those are velocity squared units, right? And then the run units are centimeters. That doesn't look like much, but simplify. The centimeter on the bottom cancels out with one of the centimeters on top and leaves us with units of centimeters per second squared. Now, we've seen units like that before. Meters per second squared, centimeters per second squared, right? Which would be centimeters per second, if you will, right? It's the same thing. So what are those units of? Yeah, they're units of acceleration. So perhaps the slope of this linearized graph has something to do with the acceleration. Certainly the units seem to lead us that way, right? The units make it look like it's an acceleration. Well, can we figure out what the acceleration of the dry ice puck is? Of course we can. We've done it before. We did it in the lab extension, right? And we're going to do it again now just quickly. We've got all the data we need. Right? In order to figure out the acceleration, well, remember, that's the slope of the velocity time graph. So now I want you to go into graphical analysis and make a new graph. Okay, and this will be a graph of velocity versus time. Velocity on the vertical axis, time on the horizontal. Right? And you'll want to follow all the steps on the front. The graph will be linear. Right? And since it's linear, I want you to then do a linear curve fit, right? So that we can see the linear regression on it, right? The linear fit of it. So take a moment here, pause, create a velocity versus time graph in graphical analysis. By the way, you've already got the velocity and the time columns there, right? You just have to change the graph so you can see it. Okay. Well, we just found a slope of our linearized velocity squared versus displacement graph with our simplified units, right, from the first part of the lab there. This was what I got, okay, and yours doesn't have to be exactly this, but I hope it's in the ballpark. If it's way off, like if you have 500 or 1,000, something's gone weird, right? It should be in this ballpark. Well, if I take my velocity time graph data, and I make a graph, ends up being linear. I do the linear fit, and I take the slope, which is the acceleration. I get about 359.7, roughly 360, centimeters per second squared. Well, compare these two then. They're not the same number, right? They're the same unit. But they are related, aren't they? About how big is this compared to that? Isn't it? It's about twice the acceleration, isn't it? If you double this, you get about like roughly 719, right? Is double that. And that's basically, it's less than 1% off from what we actually got, right? By linearizing our velocity squared and displacement data. So it looks like the slope of our linearized graph was actually 2 times the acceleration. We could write that as 2a, right, with an arrow over the a if we wished. Did your data work out that way? Does that convince you experimentally that it appears that the slope of this linearized graph is actually 2 times the acceleration? Okay, we need to remember that so that we can make a math model out of it in just a little bit here, okay? Just a little bit, we're going to make a math model out of this. Okay, so before I go and do that, I want to generalize a little bit, okay? In our lab, we did this lab so that, let me go back to here, right? So that we had a 0 initial velocity, right? You started the timer right when you cut the wire that was connecting it, right? So what would happen if that wasn't true, if we didn't have a 0 initial velocity? What would happen if we took, let's say, our ruler, and instead of putting our 0 of our ruler right at the right edge of the dry ice puck, what if we moved it down the incline a little bit, right? So that when we ran the video and the dry ice puck actually got to 0, it was already moving, right? What would that change about the graphs? This is our linearized velocity squared displacement graph, and this is our velocity time graph, right? Would that change the slopes of those graphs? Well, remember, what are the slopes related to? They're related to the acceleration. Well, is that dry ice puck going to accelerate differently depending on where you put the ruler? No. It's going to speed up just as fast no matter where you put the ruler. So these graphs will be the same slope. But what'll change? Yeah, right? The y-intercepts will change. They'll still be linear, right? But the y-intercept will change. Why? Because when it gets to 0 position and you start the clock, it now has a velocity. Remember that the y-intercept of a velocity time graph, the slope of it is the acceleration, right? And the slope up here is 2 times the acceleration, right? That's what we just found, right? We just did that whole little lab extension to figure that part out. Well, this is the initial velocity. So guess what the y-intercept is on this graph up here? Well, since the y-axis is velocity squared, you might not be surprised to find that that is the initial velocity squared. Right? It's the velocity when the displacement is 0, right? Which is wherever we put the ruler, right? It's 0 time, if you will. It's also where we count 0 time, where we zeroed out the stopwatch in our dry ice puck lab, pivot lab. Right? So this is the initial velocity squared. We could actually do this. I contemplated having you go back and redo the whole lab over again and the lab extension, but this time move your ruler down the hill, right? So that the puck was actually moving when you started recording data, but it would have taken us a day or two just to do that part. So I decided not to do that this year. I'm just hoping that that makes sense, that if it's the initial velocity down here and this is the velocity squared, it would just be the initial velocity squared here. So then let's make a math model of our linearized graph. We can, of course, use y equals mx plus b. Our y variable is what we graphed on the vertical axis, which isn't the velocity, it's the final velocity squared. Remember, v with no o means final. That equals the slope, but what did we just decide the slope of this graph is? It's 2 times the acceleration. Don't believe me? Go back and watch and redo the first part of the video, right? Do your lab sheet over again. Our x variable is what we graphed on the horizontal axis, which is the displacement, but rather than write it as delta x, I'm going to write this out. Okay, just traditional to do that. change in is final minus initial. So this is final minus initial position. Now in our lab, our initial position was 0 because of where we put the ruler. Right? So we kind of called that position in the lab extension, but it's really displacement. It's the same thing because of how we set up the lab. Right? Plus the y-intercept. Well, in our most general case, we have a y-intercept. It is the initial velocity squared. Notice this equation does not have time. Right? Yet it tells you how the velocity, the final velocity, changes when you change the displacement. Now this isn't the way the equation is actually written if you were to look it up in a book that I didn't give you. Because it's addition, and we know that both regular addition and vector addition is commutative, I can flip the order here. So that's the way you will normally see this. This is the fourth kinematic equation. It says the final velocity squared is equal to the initial velocity of the object squared plus 2 times its acceleration times the displacement. This is an equation we can use to find any of these variables without needing to know the time. Right? So that often comes in very handy, right? Where it's hard to measure the time of takes something to happen, right? Unless we're doing some high-tech pivot kind of thing, or we have some high-tech equipment like we do in class, right? So in real life, this equation can be very useful to relate these variables without needing the time. Now, I said to you earlier that I was going to be able to do this both experimentally, which is this, right, and theoretically. So let's go to the proof. Here's what we used, right? We used a linear velocity time graph, which is uniformly accelerated because it's a constant slope. Right? And we did some things looking at slope-intercept form and at area under the curve, right? And we developed these 3 equations. But all 3 of these equations have a time. So can anybody think about some algebra 2 we could do here to eliminate time as a variable? What would you do in algebra 2 if you had a set of equations and you wanted to eliminate one of the variables? Well, you actually learned several ways to do this in algebra 2. Right? I'm going to do this by using substitution. So we're going to solve a system of 2 equations. I'm going to use equations 1 and 2 because 3 just gets really complex because of the squared and everything. So I'm going to use equations 1 and 2, and we're going to take this system of 2 equations and eliminate the time through substitution. How are we going to do that? Well, I'm going to start out by taking the first equation because it's really the easiest one to manipulate. And I'm going to solve that equation for time. So here's the first equation. Right? First step to solve it for time, subtract the initial velocity from both sides. So we get final minus initial velocity equals the acceleration times the time. And then to get the time by itself, we have to, since it's multiplication, divide by the acceleration. And of course, I flipped the sides, reflexive property of equality, like to have what I'm solving for on the left. Hopefully you're okay with this algebra. Right? So if we solve the first equation for time, right? So now what are we going to do? Well, here's where the algebra 2 magic happens. We're now going to take that expression and plug it in for that time in equation 2, thereby eliminating time as one of our variables. See all this math you learned that you were like, why do we learn this math? It's because it actually helps you model what happens in the world. Right? Math is the language of the universe here, folks. And you can make predictions with your physics and your math, right, if you understand the rules. Right? So you learned all that algebra 2 so that you could do things like this in real life. So we're going to take that value for time and we're going to plug it in right there like this. See how I did that? Instead of writing a t, I wrote final minus initial velocity over the acceleration. Now you might be saying, well, this doesn't look like the fourth kinematic equation. Well, no, but we can do some algebra. So I'm going to do 2 steps of algebra at a time here. I want to move the 1/2 to the other side. How would I do that? Multiply by 2. I want to move the acceleration to the other side. Since it's divided by the acceleration, I would multiply. So I'm going to multiply both sides by 2 times the acceleration, 2a if you will. The 2 and the a will cancel out on the right-hand side, and it'll just hang out on the left-hand side. See how I did that? Move the 2 over here, move the a over there. Okay with that? Now, we have two binomials that we can multiply. And certainly you have multiplied many sets of binomials together in math class. This is actually a special set. Notice how it's the same, except this is a plus and a minus. Anybody remember what you get when you FOIL that? If you don't remember, go ahead and FOIL it, right? It'll just take you an extra step or two of algebra that I'm going to do. But this is actually what you get is called the difference of squares, right? When you FOIL this, basically the middle terms, the inner terms cancel out because you get a positive one and you get a negative one, right? So when you add them up, they cancel. So what you get is this. 2 times the acceleration times the displacement is equal to the final velocity squared minus the initial velocity squared. And if we want it to look like the fourth kinematic equation we got experimentally, I just have to add the initial velocity squared to the left to both sides, and then I'll flip the sides, right? And we get our fourth kinematic equation. Hey, look at that. So math predicts that this is the relationship between velocity and displacement for uniformly accelerated motion. But we've also seen that that's actually how it works experimentally. Right? This equation does accurately represent what happened to the dry ice puck as it went down the hill. And this, again, I know I've said it several times, right? But this is science. This is physics. Right? Being able to do something experimentally, being able to do something theoretically with math and tricks that we've learned, right, by studying math for years and years, right, of your life. And we use those tricks and we come out with results that logically and experimentally actually model the way the world works. So we can now take and drop in our right? Now, be careful. These equations only work if it's uniformly accelerated motion. Because look at our theory here, right? It's all based off of a linear velocity time graph, where the slope is the acceleration, and it's got to be linear for the acceleration to be constant or uniform. Right? If your velocity time graph is anything but linear, these equations don't work. Right? So don't get too tied up. But for us, it's as deep into motion as we're going to go. Right? We get into more general forms of motion, which really need calculus in APC. If you like that kind of thing, take APC next year. Again, these 4 equations are created so that they're all lacking one thing, which I'm going to give you a problem-solving technique tomorrow, which is going to help you see how we're going to use these to solve problems. Right? First equation, missing displacement. Second equation, missing acceleration. Third one, missing final velocity. Fourth one, missing time. Do you notice, though, that there is one variable that's in all 4 equations? Can you see it? Which one is it that's in all 4 equations? Here, 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 and here. It's the initial velocity. If you look in some books, and some professors will actually do another little bit of Algebra 2, right? And they'll create a 5th equation that doesn't have the initial velocity. You know, they'll solve this equation for the first equation for the initial velocity. They'll plug it in right there, and then they'll do some algebra to massage it and make it all nice and look cute, right? Traditionally, it's 4 equations, and I like 4. I think 4 is enough. But who knows? When you get to college, you take physics, maybe they'll do a 5th one. Okay, but it's really just more algebra to get there. So our next step here is I'm going to show you how to use these equations to solve problems. Now, you already know how to solve these problems. You've done these problems. You've just done them graphically. You've made graphs, you've found slopes, you've found area under the curves, and done things like that in order to solve these problems, right? But these equations can do the exact same thing. And those of you that are mathematically inclined are going to love what we're going to do next, because it's like you've been waiting for weeks here to be able to actually do a lot of algebra, right, instead of analyzing graphs. Doesn't mean you can't use graphs. You can use them on the test if you want, right? Sketch a little graph off on a piece of scrap paper or on the side of the test or something like that, right? But I'm going to try to show you the mathematical way of doing these things as well. But that's our next step. So I hope you enjoyed these last, what has it been, a couple of weeks almost? And the culmination of which are these 4 beautiful equations that describe uniformly accelerated motion.